Okay, we're now going to talk about convergence of sequences. And really, this is very analogous to like limits of functions. So it's like taking the limit as x goes to 0 or infinity, let's say, of f of x. So we want to see whether, if in this scenario, we would want to see if some crazy function kind of tends toward something as x goes to infinity. So this is like this is the f of x case. Whereas in the sequence case, we might have, if I use a bar graph to represent this, we might have some crazy looking sequence, but we want to see if it goes to some number L as n goes to infinity. So in other words, we ask if the limit as n goes to infinity of an is equal to L. And what this really means, the limit is, you can use the epsilon delta type thing, but this is really not needed in practice. So, but I'll just mention this anyway, just to be complete. It just means if an minus L is less than epsilon for all n bigger than some large n of epsilon. And pictorially, this is very clear from this graph here. So clearly this goes to 0. So if I tell you it has to be smaller than this, it is in fact possible to make it smaller by choosing everything larger than 1 over epsilon, for example. So for example, if this is f of x equals 1 over x, then as soon as I choose n of epsilon equals 1 over epsilon, our f does not jump out. So our f of x stays below epsilon and above 0. So after n of epsilon, this is like the this is the real line case. So if I were doing sequences, it would be very similar. Like for example, I would just use f of n equals 1 over n, and it would look very much like this situation. So in contrast, sine of n, or let's say, yes, for example, let's just try sine of n, or how about sine of x? Then here's what happens. It'll jump. So if I were trying to show that the limit was 0, then I would put an epsilon here and force it to be under epsilon. And so let's say let's say 1 over epsilon's right here, or n of epsilon. If we could find that n of epsilon, then that means it shouldn't be jump out. But it's sine, and sine jumps out. So sine of x jumps out of the epsilon range. It does not settle down. To a number, which in this case, we try to make it go to 0. It just doesn't work. So the limit does not exist. So the limit as x goes to infinity of sine x, it does not exist. And in this course, you're free to use facts like this. That does not exist. And similar, and so in this case, we can actually, the reason I brought up f of x is we can actually use limit of f of x techniques. We're actually free to use all the art from Calc 1. So for example, if the limit of our real function goes to L, if as x goes to infinity, if this is equal to L, then the limit as n goes to infinity of f of n, the sequence, this actually also equals L. So this is just saying this following very stupid fact here. This is so obvious that I almost shouldn't even mention it. But let's say let's say I have this function 1 over x. Then I plot the sequence 1 over n. This is just saying the stupid fact that 1 over n goes to 0 if 1 over x goes to 0. So it's like, this is clearly true, right? So 1 over n, it also goes to 0 as x goes to infinity and as n goes to infinity. So now that I've bored you to death with that obvious fact, let us do some examples of how we can apply this. So this is also very useful just to refresh your memory on some of these limits, because these are going to be used a ton in these courses. So let us start with an equals 2n over 2n plus 1, which we found in the last video from that example. If we want to take the limit as n goes to infinity of an, this is going to be 2n divided by 2n plus 1. So here's how you deal with things like this. You do not plug in 2 times infinity divided by 2 times infinity plus 1. That would be an indeterminate form. Instead, what you do is you factor the biggest part. So the biggest part is 2n. So it's 2n times 1 divided by 2n divided times 1 plus 1 over 2n. Do you see how I factor 2 n's from the numerator and the denominator? And so now the big parts cancel. So we get 1 over 1 plus 1 over 2n. So now you can plug in n equals infinity or whatever you want. So now I should be putting limits on both sides of the equation. So now you can send n to infinity, and this is 1 over 1 plus 0. So it's no longer indeterminate. So the limit in this case is 1. And you should be able to spot these kinds of things. Like before you do a calculation, to see where you're going, you should try to spot the limit beforehand. This is how experts treat these kinds of things. We don't really do the calculation at every time. We kind of look at it to see what it should be, and then we use the calculation to verify our heuristic. So roughly, here's how my thought process goes. What is the biggest part? What is the big thing? In the numerator, it's 2n. In the denominator, it's 2n. So therefore, cancellation. And then it's therefore 1. So that was how my thought process went. Even before doing this calculation, I knew it was going to be 1, because I always look for the big thing and to see if there's a cancellation. And this is very typical. This is a very typical kind of example. So just keep that kind of heuristic in mind. So let's do more examples. So how about an equals the nth root of n, also known as n to the 1 over n. This is also indeterminate because the base is increasing while the exponent is decreasing. And infinity to 0, it's just not defined. And there are examples where infinity to 0, the limit is actually not 1. So it's you have to verify this is 1. But actually, you can assume now that we're going to do this right now, you're free to use that the limit of this nth root is equal to 1. This will be one of the known limits that you can use for free. So here's why. If you take the natural logarithm, it's equal to 1 over n times log n. So now I'm going to write this as a fraction, and I'm going to use the L'Hopital's rule. So if I use the L'Hopital's rule, which says small over small, or big over big, these are the types of limits you can do. So it says that the limit as n goes to infinity of natural logarithm divided by n is the derivatives. So I just have to take ddn of the numerator and the denominator, in which case I get ddn of natural log and ddn of n. And I just get 1 over n on the numerator and 1 on the denominator. So then if I remember to put these limits back, then I should just get 0, right? So therefore, if I exponentiate, or rather, let me just start here. So therefore, the limit of the natural logarithms is 0. So therefore, if I exponentiate, then I should just get the limit of an should be 1, e to the 0. So therefore, the limit of n to the 1 over n is equal to 1. So, and again, this kind of thing you're free to use. Let me review another type of limit. How about the limit of 1 plus 1 over, how about x? Limit of x over n to the n as n goes to infinity. It turns out this is equal to e to the x, and you can use this. And here's why. We can actually just do the same trick, right? So just take the natural logarithm. So then we get the limit of the natural logarithm of an is equal to n. How about we remember the limits? N times 1 plus x over n. So if I now here's the trick. So I'm going to write as a fraction. So now this will be 1 plus x over n divided by 1 over n. So now I'm going to write L'Hopital's rule. Oh, I'm sorry. There's a natural logarithm that I missed here. This is important because it needs the numerator to be 0 as n goes to infinity. Remember, small over small is what works here. So it's not 0 over 0. We're going to use L'Hopital's rule. So ddn of the natural logarithm divided by ddn of 1 over n. And again, then we have limits. So this will be equal to, let's see, 1 over 1 plus x over n times minus x over n squared. That's the chain rule. And then this will mean minus 1 over n squared. So the n squareds cancel. We end up with, oh, I'm sorry, there's no minus, or is there? Yes, the minus n squareds cancel. So we end up with x, the limit of x divided by 1 plus x over n as n goes to infinity. So this is equal to x. So now if I exponentiate, the limit should just be e to the x. That's what we wanted. So there was actually another way you could have done this. I could have just changed the variables by letting 1 over n equal like y, for example. So then this would have been the limit as y goes to 0, not as n goes to infinity anymore. So then this would have been a natural logarithm of 1 plus yx divided by y. This is a little easier to differentiate because now if I use L'Hopital's rule, then it's just a ddy of natural logarithm divided by ddy of y. So then I should have just gotten x over 1 plus yx all over 1. And so this will just go to x. Very little easier, but the other way is fine too. Okay, we have that one. So how about let's see. How about 2 to the n divided by n factorial? It turns out the limit of this thing also is 0. And here's one reason why. So this is what I said, factorial is faster than any exponential. So why? So 2 to the n divided by n factorial is actually 2 times 2 times 2 n times. Whereas n factorial, you can also split it. And notice that after this point, everything is smaller than 2/3. All of these little factors here, they're smaller than 2/3. So this is actually less than 2 times 2 over 1 times 2, the first part, times 2/3 to the n minus 2. So this is also known as just 2 times 2/3 to the n minus 2. So in other words, it's this sequence here. 2/3, then you take that and you take 2/3 of it, and then it's 2/3 of that, and then it's 2/3 of that. It just keeps going down. So this goes to 0. So this is why the factorial is really big, because this 2 will eventually be dominated by the n. And you can think of factorials like. This is definitely not true, but it's like n to the n. The base roughly looks like n. And you can see that for this reason here. It's roughly speaking n multiplied n times. But it's not. This isn't accurate. It's just this is the right heuristic. So yeah. So you're also free to use this limit. Okay. So any other limits that we need to cover? I think I just want to mention one more of this form. So if I have an equals a cosine of 1 over n, this actually goes to 1. The limit exists, right? Because what we're actually doing here is we're doing cosine of 1 over big. So this is equal to cosine of small. It's not cosine of x, which oscillates. This is a pretty typical mistake that I've seen on exams, so I just want you to keep that in mind. Okay, thanks for watching.